So the next part of the discussion is the chapter which we are going to discuss is periodic table. Also we call it as periodic classification. If you go to the periodic table, what are the important points where we could classify? Actually, if you go for a periodic table, if you are going for a periodic table, this periodic table is broadly classified into periods, and it is also classified into groups, Groups are called columns. These groups we call it as columns. Groups are columns and periods are rows. Called rows. So here we have 7 periods. Periods are 7 and groups are 18. 18 vertical columns, 7 horizontal rows. So when you go for if you go for 7 periods, in the 7 periods what we can say is first one is shortest with only 2 elements, hydrogen and that is helium. Second, if you take second is a short period which we have the 8 elements. Total we have 8 elements. Here we have only 2 elements, here we have 8 elements, starting with the lithium and it ends with that is neon. Third, again short period. Here it starts with the hydrogen, lithium, sodium. Starts with sodium and ends with argon. Fourth, long, potassium. It ends with krypton. Fifth, again long, hydrogen, lithium, sodium, potassium, rubidium. Starts with rubidium and it ends with xenon. Sixth is the longest, hydrogen, lithium, sodium, potassium, rubidium, and that is cesium. And here neon, argon, krypton, xenon, and this is radon. Longest period. And of course 7th is incomplete, and because it is incomplete, hydrogen, lithium, sodium, potassium, rubidium, cesium, and last one is francium. It's an incomplete period. All this comes under the groups, all this comes under the periods. You find that the first period is shortest, second and third are short, second and third are short periods, fourth and fifth are long periods, and sixth is the longest period, and seventh is the incomplete period, which we have to notice. And you are finding that every period in a period the starting element they belong to alkyl metals, bending elements belongs to noble gases, ending elements belongs to noble gases. You can notice that because this is helium, neon, argon, krypton. Next one is xenon and radon. You can notice that every period is ending with a noble gas and it is starting with a alkali metal. So if you go for groups, there are total 18 groups are there. In these 18 groups, you can find that these groups are again, let me say, they are classified into blocks. Groups are classified into blocks. Blocks are classified into 4 subtypes: S block elements, P block elements, D block, and also F block elements. Again, S and P block, S block and P block together, we call them as representative. We call them as representative elements. D and F block, D block elements are otherwise called transition elements, and F block elements are inner transition elements. And D block elements are called transition elements, and F block elements are called inner transition elements. If you go for S block, again this representative elements. If you go for these representative elements, particularly in this S block, you have 1A alkali metals, and 2A alkaline earth metals, alkaline earth metals. Likewise, if you go for P block, if you are going for a P block, then you are finding that P block is made up of 13th group. Also they are made up of 13th group, 14th group, also made up of 15th, group, then also they are made up of 16th group, also they are made up of 17th group. 13th group we call it as boron family. We call it as boron family. 14th group carbon family. 15th group we can call it as nicogens. 16th group you can take oxygen family. And 17th you can take it as halogens, and 17th you can take halogens. 18th group if you take, these are noble gases. Yeah, 15th group nicogens, 14th group carbon family, and 13th group that is boron family, and 18th group we can call it as noble gases. and so on and so forth. So if you look into the design of the periodic table, what you are noticing here is the periodic table more or less looks like this. That is, let me put it in this way: hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Then beryllium, magnesium, calcium, strontium, barium and radium. Then scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. If you take, then we can take here, this is potassium is 19 atomic number, calcium 20, 21 scandium, 22 titanium, 23 vanadium, 24 chromium, 25 manganese, 26 iron, 27 cobalt, 28 nickel, 29 copper, 30 zinc, 31 is gallium, 32 is germanium, 33 is arsenic, 34 is selenium and 35 I think it's going to be, that is bromine. 35 is going to be bromine. So what we are noticing over here is like in particular rubidium 37, strontium 38 and cesium 55 and barium is 56. This is 55 plus 32, 87 and this is going to be 88, 11, 12, 11 atomic number, 12 atomic 3, 4 and this is 1. So what we are just trying to understand here is very simple method. Practice always makes you perfect. Practice always makes you perfect in remembering the elements in the periodic table. So here if I just draw a horizontal line like this, and if I cut off the one more horizontal line like this, then I can say that all this comes under, that is P block, this comes under S block, this comes under S block, all this comes under S block, this comes under D block and this comes under, that is P block. Here of course if you go for the beryllium, lithium beryllium, then boron aluminum, I think here I can take boron, here I can take here boron and this is aluminum. Likewise again I can take carbon, silicon, germanium, I can take nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, fluorine, chlorine, bromine, boron, aluminum, gallium, indium and thallium, carbon, silicon, germanium, tin and lead, nitrogen, phosphorus, arsenic, antimony and bismuth, oxygen, sulfur, selenium, tellurium and polonium, fluorine, chlorine, bromine, this is bromine, fluorine, chlorine, bromine, iodine and astatine. All this comes under, that is, this comes under P block. This is P block. And here boron atomic number is 5, 13, 31, 31 plus 18, 49, 49 plus 18, the 49 plus 32, 81, carbon atomic number 6, silicon 14, germanium 32, 10, 50, this is 82, 7, 15, 33, 33 plus 18, 33 plus 18, I think it is 51, 51 and this is going to be 83. Oxygen atomic number is 8, sulfur 16, selenium 34, tellurium 52 and polonium 84. Fluorine atomic number 9, chlorine 17, bromine 35, iodine 53, astatine 85, and so on. This comes under the P block. So likewise, if I am joining this order in the same pattern, in the same fashion, you are finding that here yeah, so scandium 38 is strontium, 39 is yttrium, 40 zirconium, 41 niobium, 42 molybdenum, 43 technetium, 44 ruthenium, 45 rhodium, 46 palladium, 47 silver, 48 cadmium. Here, so here you are going to get zinc, cadmium, mercury is 80, copper, silver, gold is Au 79, nickel, palladium, platinum 78, then cobalt, rhodium 77 is iridium, then iron, ruthenium, osmium 76, 75 I think it is rhenium, then here 56, 57 is 57 lanthanum, 72 hafnium, 73 tantalum, and 74 I think it is tungsten. So similarly here also what we are noticing is 89 is actinium, 104 rutherfordium, 105 dubnium, and so on. So it's an incomplete period, and so on. So what is happening here is like 75 so it's 44 ruthenium, 45 rhodium, 46 palladium, 75 rhenium. Yeah, I think so. This is D block, and what you're finding is like this is, as I told you, this is 1A group alkali metals, 2A group alkaline earth metals, and this is 3A group boron family, 4A group carbon family, 5A group nitrogen family, 6A group oxygen family, 7A group halogens, and this is 1B, and this is 2B, and this is 3B, 4B, 5B, 6B, this 6B, and this is 7B, 6B, 7B, and this is together 8B, and I call this as 8B, I call this as transition triads. I call this as transition triads. The most electropositive element, most electropositive element is cesium. Then the lightest element is hydrogen. Zinc, cadmium and mercury, these are and mercury is the only metal, it's a liquid metal. Mercury is the liquid metal. Bromine, if you take bromine, liquid non-metal. Liquid non-metal. These three elements, liquid metal, and 2b, these are called typical transition elements. Typical transition elements. 1b, if you take, these are noble metals. 1b, noble metals. Sodium and potassium, sodium and potassium, if you take particularly potassium and rubidium and cesium, these three metals, potassium, rubidium, cesium, they are used in photoelectric cells. S block elements are metals dominated. P block elements are both metals and non-metals. If you take D block elements, if you take in particular D block, they are made up of both, they are metallic, also they are amphoteric. They are metallic as well as they are also amphoteric. And these are typical transition metals. And tungsten, this is called tungsten, otherwise wolfram, is used as a filament in electrical bulbs. And so on and so forth. This is a complete picture. And F block elements, let me finish off F block elements also. If you take F block elements, you can see a break here. 57 is lanthanum. I'm just highlighting here. 57 is lanthanum. 89 is actinium. 104 is rutherfordium. So you can see a big break in between this two set of elements. So you can take, that is 58 cerium to 71 lutetium and 103 lavranthium, 103, sorry, this is 90 thorium, 90 thorium to 103 lavranthium. This comes under F block elements. 103 lavranthium, 90 thorium to 103 lavranthium, and 58 cerium to 71 lutetium comes under F block element. So the next part of our discussion in the periodic table is let us discuss something about the various contributions made for the development of periodic table. And before that, in the previous class I have given you a detailed description of how the periodic table looks, and this periodic table, how we have classified them into blocks, and how we could able to separate the different blocks of elements of the periodic table into S block, P block, D block and F block also. The discussion went on. Now we enter into the contributions for the development of periodic table. That is, let us begin our discussion with, I'll put it like this, contributions of development of periodic table. I would like to highlight the first contribution, that is law of triads, which is given by the J.W. Duberner. Law of octaves, given by John Newland. Third one, Mendeleev's periodic table. Mendeleev's periodic table, given by, that is, Mendeleev. Fourth one, that is Moseley's periodic table. Moseley's periodic table, if we take, okay, based on the Moseley. Fifth one, modern periodic table. Modern periodic table given by Niels Bohr. So all these are the various contributions for the development of periodic table. In this law of triads, law of octaves, Mendeleev's periodic table, Moseley's periodic table, and modern periodic table. Here in this, the periodic property is the, that is, average arithmetic mean. Here the periodic property in J.W. Duberner's law of triads, that is, periodic property is average arithmetic mean, and we go for law of octaves. It was proposed by John Newland, and the periodic property, according to the periodic property for law of octaves, it is octave of music. Octave of music is a periodic property. For Mendeleev's periodic table, periodic property is atomic weights, and for Moseley's periodic table, the periodic property is the atomic numbers, and for modern periodic table, the periodic property is electronic configuration. So based on this, we would like to have a detailed discussion about each and every concept here in the periodic table. So one by one, let us have a discussion about this different contributions and different theories for the development of periodic table. Let us have a detailed discussion for this, and let us start with law of triads. So let's start our discussion with the law of triads. That is, number one, law of triads. It states that significance, the atomic weight of middle element is average arithmetic mean of other two elements of same group is law of triads. That means we are calculating the atomic weight of the middle element, which should be equal to the average arithmetic mean of the other two elements belonging to the same group. Suppose for example you take 1a group. 1a group is alkali metals. So I am taking here, that is lithium. We have hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. So I am taking lithium, sodium and potassium belonging to the same group. So you take lithium, you take lithium atomic weight. Lithium, if you take lithium atomic weight is 7, sodium atomic weight is X, of course atomic number of lithium is 3, potassium atomic weight is 39 and atomic number is 19, sodium atomic number is 11. So if you want to calculate the atomic weight of the sodium, X is equal to 7 plus 39 divided by 2, which is equal to 46 by 2, which is equal to 23. Here 23, therefore X is the atomic weight of sodium, average atomic weight of sodium, which is equal to 23. Like this you can take even one more example. I will take example 2 if you want, that is iodine. If you take, that is halogens, you take halogens, fluorine, chlorine, bromine and iodine, of course astatine. So I am taking here chlorine, bromine and iodine. So chlorine atomic weight is 35.5, atomic number 17, bromine is X, 35 atomic number, and iodine 53 and it is 127. So X is equal to 35.5 plus 127 divided by 2. So 127 of 35.5. So this is 5 decimal, this is 12, 156, 162. 162 means this is going to become 162.5. So X is going to become 162.5 divided by 2. This is 81.25 is the atomic weight, is the average atomic weight of bromine. So this is how we can calculate the average atomic weight of the middle element of the three elements, triads of the elements which are picked up from the same group. If you want to calculate the atomic weight of the middle element, we can calculate in this procedure. So here in the alkali metals, if you pick the triads, lithium, sodium, potassium, the sodium is going to become the average atomic weight element, which is in the middle. Its atomic weight after calculation is 23. Similarly, among halogens, fluorine, chlorine, bromine, iodine and astatine, we are picking three elements, chlorine, bromine and iodine. Here bromine is the middle element, so bromine is equal to the atomic weight of the average atomic weight mean of the other two elements. So 35.5 plus 127 divided by 2. After simplification, it's going to be 81.25. So actually, numerically, when you are calculating the atomic weight of bromine, it is 80. But because we are saying average atomic weight, it is accurately, the value is very close to 80. That is 1.25 times 1.25 value. Extra is, it's extra compared to the original value. But then this is how we calculate the average atomic weight of the given elements from the triads of the same group. So the next part of the discussion is, that is law of octaves. So if you go for law of octaves, as it was proposed by John Newland. So if you're taking the set of elements like let's begin with the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Similarly, if you go for that is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. and argon. Of course, you can take even next element, that is potassium and calcium. If you take, what you're noticing is this is 1A group, this is 2A group, 2A, and of course this is 3A, this is 4A, this is 5A, 6A, 7A, and 8A group. What is interesting here is, what we have to note here is, noble gases are not included in properties of elements. Noble gases are not included in properties of elements. Then octaves, law of octaves is not applicable. Okay, law is not applicable. Beyond calcium. Law is not applicable beyond calcium. Then if that is the case, because noble gases are not included, so I am striking off the noble gases and I am starting with the lithium atomic number 3, 4, 5, 6, 7, 8 and 9. For 9, again you take here 11, 12, 13, 14, 15, 16, 17, and this is 18. So 1, 2, 3, 4, 5, 6, 7 is the 8th element. If you count the elements 1, 2, 3, 4, 5, 6, 7, 7th, the 8th element is sodium here. So lithium and sodium, if you take the atomic number differences, the difference of 3 and 11, that is 11 minus 3 is equal to 8. Again here also, again here if you take potassium is 19, potassium atomic number is 19. So if you take 19 minus 11, which is equal to 8. So this 8 is octave of music. So therefore we can just take this number 8 is nothing but octave of music. So if the elements are arranged, if the elements arranged in increasing order, upward arrow represents increasing order. Elements arranged in increasing order, upward arrow indicates increasing order. Elements arranged in increasing order of their atomic numbers. The 8th element starting from the first, 8th element starting from first element is in octave, octave of music, atomic number, and this is element. So this is the statement which is given by law of octaves, and it is applicable only, it is the cutoff, it is not applicable. Calcium is not applicable in the law of octaves, and noble gas also they are not applicable in the law of octaves. So from this law of octaves we can understand that the first starting element and the ending element, set of 8 elements are there, 1, 2, 3, 4, 5, 6, 7 and 8th element. Again 1, 2, 3, 4, 5, 6, 7 and 8. The 8th element and the first element are always in the octave of music, and it is the difference, you are finding that the 8, their atomic numbers difference is 8, and this is how the law of octaves can be understood in terms of octave of music. So this is law of octaves. So the next part of the discussion is, that is Mendeleev's periodic table. So here periodic property, atomic weights, atomic weight. So all the physical and chemical properties, all the physical and chemical properties of elements, all the physical and chemical properties of the elements are periodic. Functions of their all the physical and chemical properties are the all the physical and chemical properties of the elements are the periodic functions of their atomic weights. So Mendeleev has taken the atomic weights into consideration while placing the different elements in the periodic table. In fact, if you go for Mendeleev, the short form of periodic table, PT, stands for periodic table. It contains 6 periods and 8 groups. In fact, this is short form of periodic table. Long form of periodic table, according to Mendeleev, long form of periodic table contains that is 7 periods and 18 groups. 7 periods and 18 groups. However, there are some limitations. in the periodic table. If you go for the limitations of periodic table, if you take limitations, no exact position for hydrogen in periodic table. Second, no place for isotopes. No place for isotopes, and also atomic weights of elements, position was irregular. That is, anomalous pairs ambiguity was not explained significantly. One example I would like to give you: if you take potassium, if you are taking potassium, that is, for example, let me put it in this way, that is lithium, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Again, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. And next is, that is potassium. Potassium is 19, atomic weight 39, argon 18, it is 40. So you are finding that this is the set of elements. They belong to second period, and this set of elements, they belong to third period. And you are finding that potassium belongs to fourth period. But what is interesting here is 18 argon 40 and 19 potassium 39. Because the atomic weight of argon is 40, it is supposed to be placed in the position of potassium. Because the argon atomic weight is 40, because the argon atomic weight is 40 and potassium atomic weight is 39, the potassium should occupy the argon position. The potassium should occupy the argon position, and the argon should occupy the potassium position. But in the periodic table, you find that their places have been exchanged. The places have been exchanged, and of course, there is a justification saying that argon is placed below the neon in the periodic table just because argon and neon, both of them are noble gases. So they will have some reactionality in the chemical properties. Might be it is because of that reason the argon would have been placed below nitrogen. But if you take exactly according to the definition of the Mendeleev's periodic table, definitely potassium will occupy the position of argon, and argon will occupy the potassium, and argon will occupy the position of the potassium in the periodic table, and potassium will occupy the position of argon in the periodic table. So that's why this pair of I can say that 19 potassium 39 comma 18 argon 40 are anomalous pairs. Such anomalous pairs were not properly explained by the Mendeleev's periodic table, were not properly justified by the Mendeleev's periodic table. So next part of discussion is, that is Moseley's periodic table. So here periodic property. The periodic property according to the Moseley's periodic table is atomic numbers. You know very well that atomic number of an element, atomic number of element is given by the symbol Z, and it actually represents the number of protons present, in the nucleus of atom, and apart from this, if you go for the significance, that is significance or the statement significance, if you take all the physical and chemical properties, all the physical and chemical properties are the periodic functions. All the physical and chemical properties are the periodic functions of their atomic numbers. In fact, Moseley's experiment with the X-rays has given the expression mu bar is equal to under root of mu is equal to A of Z minus B. This is the mathematical expression where mu is the frequency of X-rays, and Z is the atomic number of element, and A comma B are the physical constants of element. Physical constants of the element. So the next part of the discussion is, that is modern periodic table. Next part of the discussion is modern periodic table. In this, the periodic property, if I take, the discussion goes on, periodic property, if you take, that is electronic configuration, EC, electronic configuration. What is EC here? This is the electronic configuration of elements. Electronic configuration of the elements. Next, what is the significance? Same definition almost. Significance, all the physical and chemical properties of elements. The elements are the periodic functions of their periodic functions of their electronic configuration. All the physical and chemical properties are the periodic functions of the elements are the periodic functions of their electronic configuration. So in this modern periodic table, we would like to have few more points under discussion. And this modern periodic table was actually proposed by Niels Bohr. It was proposed by Niels Bohr.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.